So here we have vector f. Sometimes in physics, we want to know how vector f behaves in just the x or just the y direction. We call this finding the components of the vector. And you can see over here on the right, we have a coordinate system that will come in handy later, but for now, we'll just leave that be. But on vector f, the x component looks something like this. So it's the part of f that's just in the x direction. And the y component of vector f looks like this. Just the component in the y direction. And let me label those a second. So that's fy, and that's fx. So what we're going to do here to determine the components of vector f is to use what we call SOHCAHTOA. And really, for the most part, we will only need SO and CO out of this, but it's good to have the whole thing there just to try to remember it. So to figure out what goes with which component, we can start to use our SOHCAHTOA. So we have our angle theta here, and where that is located is very important. So first we could look at sine. And we know that sine is the opposite over the hypotenuse. So what that means for us is that sine of theta is the opposite side. So if we have theta here, then the side opposite theta, the one that doesn't touch theta, is fy. And the hypotenuse is just f, the magnitude of the vector. So if we solve this whole thing out, we get fy equals f times sine of theta. We can do something similar for the x component. Instead of sine, we have cosine. So we end up with cosine is adjacent over hypotenuse. So just make ourselves a little more room here to write. So if we go through the same process, we can see that cosine theta is the adjacent component. So here's theta, and the component that's touching theta is the adjacent one, so that is the x component, fx. And then divided by the hypotenuse again is just the magnitude of the vector f. So solving that out, we get fx equals f times cosine of theta. So let me just box those a second. Now we can't guarantee that this will always be true. That means we can't guarantee that f will always be cosine, fx will always be cosine, and fy will always be sine, but we do know that the adjacent side to whatever angle you have will always be cosine. So if you have your angle here, the adjacent side is always cosine. If the angle location changes, that will change. And the opposite side is always sine. I said before we are going to take into account our coordinate system up here. This tells us which direction is positive for x and y, so it's telling us x is positive going to the right, and y is positive going up. So we need to check our components to make sure we have the correct sign for our coordinate system. So our fx component goes to the right, so it should be positive, and it is. Our Fy component goes up, so it should be positive, and it is. It's important to note that you can have really any coordinate system you want. This one with x positive to the right and y positive up is kind of standard, but there's nothing stopping you from putting x positive to the left and y positive down. For this same vector with that different coordinate system, the magnitudes of the components would stay the same, so Fy would still be sine theta and Fx would still be cosine theta, but both of the components would now be negative. We haven't changed anything about the vector, we're just changing how we keep track of everything, which is what the coordinate system does. So, let's go do another example. We'll leave that one there. How about this one here? So let's do the same thing we did before. We always like to draw triangles around the vectors because that helps us keep track of everything. I'm just going to draw the whole triangle in green here. And then label the right angle there. So we can do what we did before. We can take the side that's adjacent to theta, which is the side over here, and call that cosine, because we know that the adjacent side goes with cosine from SOHCAHTOA. So that's Fy here. So we can have Fy equals, and I'm going to leave a little space to account for our signs later, the magnitude of the vector times cosine theta. And if we do the same thing for the x component, which is here, which is opposite theta, so theta's here, we're on the opposite side, now we have Fx equals F sine theta. I told you we needed to check our signs, so let's look at Fx first. To add a vector on it, it looks like that. Fx is pointing to the right, and for the x direction, the right is positive, so this is positive F sine theta. For the y direction, though, our y component points down, but our positive y direction points up. So what that means for us is that our y component here is negative. So there's a couple things that's different here from our first example. Let's see if I can't zoom out and get them both in here a little bit. There we go. In our first example, x was cosine and y was sine. And over here, we have x is sine and y is cosine. So you can't just follow some rule that always says x is cosine and y is sine. That only works if you're given the angle from the horizontal down here. So pay attention to where your angle is located because it can change things. Also, over here, we had all positive components. And we can kind of see why that's true, because if we draw our vector f on this coordinate system with the tail of the origin, it's pointing up and to the right, into the quadrant where both x and y are positive. So both our answers were positive. Here, it's a little different. Our vector points down into the right. So again, if we put the tail at the origin, we would see our vector pointing down there into the fourth quadrant, where x is positive, just like our answer, and y is negative, just like our answer. So this is the basics of it. You can do a few extra tricks if you actually have the magnitude of the vector and the value of theta to start plugging in to calculate actual decimals. But for now, this is the basics of it. The big things are draw your triangle and label the sides that are opposite the angle and adjacent to the angle, keeping in mind that these depend on where the angle is, and the angle won't always be in the same place. And then from there, your adjacent component is cosine, your opposite component is sine. Always have the magnitude of the vector in there, and then make sure you account for the positives and negatives as determined by your coordinate system.